Fancy pants. We're coming on in, and let's see. Welcome. Oh no, what's going on with my shirt? I got like some crazy green screen shirt thing going on. Ah man. Okay. Well, for all the technology, I've got like space age Matrix shirt on today, so we'll do that. All right, we'll just live with it today and carry on smartly. Okay, let's see. Welcome. Let's kick off and see if we can get the right slide deck showing today. Super. And here we go. Okay, so welcome back. As you know, we are in Westmont College. We're live in Santa Barbara, down in Winter Hall. I'm Professor Patterson. This is Computer Science 30, our second programming class. This is part of a 5-week seminar series, and today's lecture is scheduled for 2 hours. We're communicating live in real time for those of us on the Slack channel on hashtag broadcast questions. We have one student who's on a train, we think, and we have one of our remote students is in class with us this morning. Good morning, Nick. How are you doing? And of course, our normal studio audience. So great. So welcome. We're starting week 3, and this is the week when stuff starts to change. We're kind of getting past the basic structure of the language and starting to talk about Java collections framework. And this is a shift that I really like. I like when we start talking about the data structures and how we can work with it. So let's make sure we're ready to participate and make sure notifications are off. Got mine off. Checking my pockets and everything else. We've been opening our class each day just thinking a little bit about the role of technology in regulating behavior, thinking about the ways in which we have legal regulations that control our behavior, and sometimes we encounter those with our technological work. But we also brought up the fact that legal regulations aren't the only thing that regulate our behavior. Social norms are something else that regulate our behavior. I thought I'd just sort of open up for a second to kind of get some feedback from you guys about what is the current social norms around smartphone usage. Social norms are something that we're always negotiating, and I'm always interested to have these conversations with you guys about what is it like to deal with your friend groups and working with phones. Do you have rules that you guys have with your friends about when it's okay to use smartphones? And so what's not okay? What's a not okay situation?
Just sometimes when you're trying to have time together and everyone's just on their phone, like for example when you're dining out, like I find my friends and myself included, just on our phone at one point silent. So sometimes like one of us says, "Hey, get off your phones right now."
So you kind of, but you have to have someone actually. You're in the restaurant, everyone's on the phone. Someone actually has to say it though, right? So it's sort of like trying to get it out. Do any of you have like times or zones that everyone understands you don't use your phone at this time? What? So your family has rules? Uh-huh.
So I'm pretty like strict about it with what I feel. Like I don't really force people to adhere to my standards, but I really hate it when I'm trying to talk to someone and they are on their phone. Or I hate it when I'm in a group hanging out with people and there's like one person or two people that are just like like videoing everything and doing like social media stuff instead of just hanging out.
Well, so that's a slightly different question. What about rules for sharing pictures of you on social media? Like, is it okay for people to just Snapchat you, or how do you guys work with that?
The social norm is yes, it is okay. I say if I like you and I like your audience on social media. I had people like
Wow. So
sending
you
me like happy birthday messages, and I was like, oh hey, who told you it's my birthday? And they were like, oh yeah, we saw this person's story on whatever Instagram or Snapchat. I'm like,
Yeah, it's
right.
tricky, right? Because if someone takes your picture, whose is that?
I
Is
have
that
no
is that
idea.
you because it's your image, or is it theirs because they took the photo?
It's
Definitely yours. But like in terms of social norms, you guys don't like it being shared, but you kind of constantly have to be renegotiating and saying what is okay for my particular usage because it's not built into the technology, right? There's no way that you have to technologically request permission. It's also kind of not legal. I mean, maybe there's some kind of like way that you could legislate it, but basically, like, there's no law about sharing a photo of someone else on social media. I suppose if you started making money on it, there might be sort of, not ways to get around it, things like that. All these things are kind of norms, though. They're not things that are legislated, and so we're always trying to figure it out. In our house, we definitely don't use phones during meals, that's for sure. And I think that there are different times when we have conflict in our house because we're trying to organize something, trying to talk about something, and some people won't kind of be there because they're on their phone. They're physically there, but mentally they're not there. And I know I have these situations where I start getting really upset because we're trying to figure out when we're going to leave, what we're doing this weekend, and we can't get everyone's input. And it depends on my mood, but it kind of can drive me really crazy sometimes. Drive me nuts. Um, but I think generally in our family we negotiated okay, and I think that at least in my peer groups, um, most of the time people don't use their phones very much in social settings. I think that kind of maybe as you get more professional situations, maybe. I mean, I'm also tend to be in situations that are more, like for example in church. It's really social norm is really inappropriate to use your phone during church unless you're reading the text or something on your device. I think the same with chapel. I think people are always kind of using their phones on the sly in chapel, but it's definitely not okay, right? Like it would not be unexpected to have someone call you out for it. Um, but you see people walking around with it all the time, so that's kind of okay. It's totally okay to do it when you're walking between locations, a different situation. Yeah, so some of the ways in which our behavior is regulated around smartphone usage, but everything as well, right? It's not okay for you to reach over and check the time on someone else's phone, right? That would be weird, I think, right? Like if your phone's on the table and someone else kind of grabbed it and did Siri or checked the time, would that be sort of out of bounds? Feels
Our
weird.
friends do that though.
If
Like
it's
if
like
we're like
funny, yeah.
sitting and do you see like our phones are on the table? I've seen someone just like press the home button just to like see what time it is.
So that's okay.
It's like a close friend, I guess, and it's
Yeah,
like
it,
it's
you would
like
have to be
something
a
that's
close
like
friend.
funny and like
It'd be a little bit weird if some random person just
yeah.
walked up and touched my phone.
Yeah, right. So okay, there you go. That's a little weird. So it's okay if it's someone close to you, but random strangers don't get to touch your phone, right? That's a little weird, right? Have you ever gone to like a vendor, kind of a small business vendor, maybe in a market or something, and they're using Square or some kind of digital payment system on their phone, and they give you their phone in order to sign with your finger? Like that always feels a little weird to me. It feels to me like they've given it's like they've handed me their toothbrush and they want me to sort of like wave the toothbrush. It sort of feels like I'm touching something that like I'm kind of not comfortable touching of theirs. Like it's in their pocket.
Phones have more germs than like toilet seats.
They hold it up against their face and stuff, and now they've just handed it to me to sign. There's some social weirdness about that to me, and it's not clear what that's coming
What
from.
about like the cash register iPads, so like the iPads that you can flip on a swivel and
Yeah, I guess at first that felt a little uncomfortable to me, but because that's not someone's personal phone, that doesn't feel quite as awkward. Lawrence Lessig, who's the guy I'm channeling here, has this great book called Code and Other Laws of Cyberspace, and he talks about regulation, and that's where I'm getting some of these ideas from. So he talks about legal regulations and social norms and regulations around that. There are a couple other ones. We'll keep talking a little bit about some regulations going forward. Okay, so for our class today, we've got some administration. All right, we're in week 3 of the 5-week class, and the pace is going to ramp up this week pretty heavily. I don't know if you've noticed or not. But we've got a quiz on chapter 5 today, 6 on Wednesday, and 15 on Wednesday too. Now, the fact that they're both due on Wednesday is just because I already put 6 out. Really, you should be getting 6 done before Wednesday. We've already covered the material. And if you're waiting till the last minute, that's going to be rough to do 6 and 15 in the same day. 5 is decisions, 6 is loops, and 15 is Java collections frameworks, which we're talking about today. There's also a programming assignment on 6 due on Wednesday, which is the building a pyramid in JMonkey Engine. And so taking what we did last class and then building your own pyramid out of it. And we have an exam on Friday. So the exam on Friday is covering, it's in Canvas, it covers up through 15, chapter 15 of what we've done so far. And one of the things we've got to iron out is how our remote participants are going to take the exam. And I'm having a meeting this afternoon. We'll get some more information about how that's going to work out. It's probably going to be an exam that's looking to last maybe about an hour, but we'll take the whole class to do it. And I need to figure out a little bit of the details of that because of how we've been progressing in the class so far. Weekend after that, we've got an assignment on Chapter 15 due. Chapter 15's assignment is around the Java collections frameworks that we're talking about today. So it wouldn't hurt to look at that before the exam as well, but just because of time. Okay, so last time we took a look at the transition from while loops to for loops. For loops we saw was this particularly structured way of doing an iteration over some number of times or some condition we're looking for. It just is a convenient way to do many of the things that we do in a while loop in one particular line of code. There's an example of it down here on the bottom. For int counter equals 1, while counter is less than or equal to 10, counter plus plus. So that's going to run through that loop 10 times and print the numbers 1 through 10, each on its own line as a result. We also took a look at JMonkey Engine and looked at how we could use that in order to do some 3D graphics worlds. And there's an example of doing some boxes. And then we put loops into JMonkey Engine to iterate over space and put boxes at different locations. So if we were to use this loop, it would be as if we were using counter as a location to place the boxes. Instead of printing out each number, we would create a new box and add it. And then we ended by talking about common loop algorithms. We looked at about 3 of them. I think we looked at sum, average, and counting matches, if I recall correctly. There's a nice chat section in our textbook that goes through some of those common loop algorithms. That would be a great thing to make sure you understand well, because it's a really common set of actions that you do in real code, in real jobs all the time. But today we're moving forward and we're talking about Java collections framework. And I mentioned that this is something I like this transition because this is the moment at which we start talking about bigger picture issues of programming and how we keep track of data. And so what I'm presenting here is a whole bunch of different classes that are available as part of the Java collections framework. Now, strictly speaking, the red ones on the bottom are the ones that you can instantiate, meaning you can call new on them and the constructor associated with them, and you'll get back a reference to a class. So ArrayList, stack, LinkeList, priority queue, hash set, tree set, hash map, tree map, those are all objects that you can create. The white boxes are interfaces, and those aren't classes that you can create, but they're a collection of methods that everything below them implement. So it's as if saying, well, there's some things that ArrayList, stack, and LinkeList have in common. And those things that they have in common, we're going to give them the label list and say, okay, everything that is a list has these things in common. Everything that's a queue has these things in common. And even though you can't create a queue from using the new keyword, you can talk about your variables as if they were queues or lists or collections or sets. The ones on the left, the ones that are children of the collection interface, are all various kinds of ordered groups of objects. It's called a collection because it's a collection of data. And they're collections that are ordered in different ways, in lines, or maybe consider it like in a bag, or different ways of thinking about it. And then map is a slightly different one. Map is sometimes called a dictionary or an associative array. In JSON, it's an object. And a map is where we create relationships between two objects and then put those together, those relationships all together. And these are general data structures that are used in all kinds of applications. And the reason we learn them is because trying to find the data structure that aligns best to our problem is one of the skills of thinking computationally. Trying to understand what is the nature of the data that I'm working with, and what is a data structure that models that data well. So let's walk through some of them. Let's walk through all of them and try and talk about them just to give you an overview of what we're talking about. And then we're going to try and work with some in code in Eclipse. All right. So starting with collection. Collection is our highest order on the left side. Collection is an interface, and so that means that we can't instantiate it. What it has, or what an interface means, is that there's a whole set of methods that its children must have. So it's kind of like describing a class and putting all the methods that are in that class, but you don't actually fill them out. You just leave them there and say, everything that's a child of this interface must therefore implement them. So what are some examples? So each collection has a constructor. That's not a property of a collection per se. That's a property of all objects. But a collection, you can add things to them. So regardless of what collection you have, all of them have to implement the add method. And depending, the X is the thing you're adding. You could also remove elements from the collection. Okay, so that's things that all the collections have in common. You can check to see whether your particular collection is empty. So your collection of objects may or may not be empty. It also has a size, so you can check to see how many things are in your collection. All of the collections can be converted to a string representation by calling the toString method. And like a constructor, this in particular isn't a method that's associated with collection, but it's associated with object, which is the parent class of all objects. But collections do have them. You can also ask whether or not a collection contains a particular element as well. So that's important if you're trying to understand whether something that you're keeping track of is present, if you're going to work with it, if you can find it. And then the last thing that each collection has is something called an iterator. And an iterator is a object that enables you to walk through all the elements in your collection in an efficient way, typically in a loop, but not necessarily. So these are general methods present for all the different children of collection. How they actually get implemented varies based on the paradigm of what the specific concrete classes are designed to represent. So the next one we've got, let's see, sorry, that's a duplicate. So the next one I want to talk about is list, and list is also an interface. And list has everything collection has, because it's a child of collection, but it also adds some additional things. So it kind of constrains the collection or adds particular ways of thinking about collections that are lists. So lists have to be ordered, and in a linear sense, like there is an ordering in a list. Everything that you put into a list exists in a particular order. Something comes before. If you put something in a list and you put something behind it in the list, that order is respected, and you can find out about that order by calling other methods. Remember, when we encapsulate stuff in an object, what we're doing is we're trying to capture a behavior by making the constructor and each of the methods that we have work together in order to create some kind of way of thinking about data. So a list wants you to think about data as an ordered set. So if you think about this as maybe books, if you were to think about it as books, these would be books on a bookshelf. You have several books, they're in an order. When you put them in order, they stay in order. You can check out that order. List is an interface though, and there are two particular implementations of lists that we can use. We can do an array list, and we can do a linked list. Both of them implement all of the methods that are required of list and all the methods that are required of collection, but the way they do it is different, and as a result, some of those methods are faster than others. That's an important part of why, an important decision about why you might use one implementation over another, or why you might make a new implementation as well. In each one of those implementations, ArrayList and LinkeList has pros and cons, mostly related to the speed and efficiency of particular operations within that interface. Nick? So a linked list, and I'll have a graphic of it in a second, but a linked list is, you can, maybe as a metaphor, you can think of it as people holding hands, where each person is the data that you're keeping track of, and as they hold hands together, they form a list down the line, like if they're on a beach or if they're in a playground or something. You could also think of it as a chain, where each piece of data is one of the links in the chain, and they connect together by grabbing onto hands along the way. And then in contrast to that, an array list, again, I'll have a picture of this in a second, but an array list is more like a carton of eggs. where instead of people, we're talking about eggs, and you put an egg into the carton, but when you start, the carton has 12 slots. And so because you start with 12 slots, you can put 12 eggs in it, and then if you want to put a 13th egg in it, you need to get a new carton. And you get a carton with 24 spots, and then you put them in. So that sort of represents the way that the memory is managed underneath in the implementation. And as a result, it's very fast if you want to add a new element to a linked list, because people holding hands just have to let go of hands and grab onto the new person they want to have it added. But if you want to add a new egg to an egg carton, remember in a particular position, because that's what lists do, you have to pick up every egg and shift it down into the next slot. So adding things to the middle of an egg carton or an array list takes more time, but adding things to the middle of a linked list takes less time. But an array list is faster because you can go to a specific element in the carton faster. A linked list, you have to walk down the chain of hands to find the one that you're looking for. In a carton, you can just go directly in. So pros and cons. Okay, so in contrast to a list, a set is also, well, not in contrast, like a list, a set is also an interface. But unlike a list, what it's an interface for is a different kind of behavior. When we think about sets, what we use them for is to keep track of collections of unordered and unique elements. So if we think about a group of people holding hands in a line, they have a particular order because they're all holding hands, and by holding hands, they're creating an order. Or if you think about books on a bookshelf, they're in a particular order. But what a set is designed to do is to keep track of things where you don't care about the order. So this is more like throwing books into a big bag, and you're not really keeping track of the order of the books. You just need to know which ones are in the bag and which ones aren't in the bag. Or maybe, I don't know, students in a classroom. You know that the students in the classroom or they're not, but you don't care about the order necessarily. So you would use this to keep track of, one example that's used in the book is what we can keep track of in sets is the colors on a flag. The colors on the flag, if you think about them, the American flag, red, white, and blue, you don't really care about what order the colors on a particular country's flag are, because when you're keeping track of colors, you just care about whether a color is used or not used. To talk about the order of a flag color doesn't really make sense. So we use a set in that situation. And because we are able to let go of the requirement of keeping track of order, sets can be much faster than lists, as long as you don't need that ordering information. But because we don't have ordering information, sets can only keep track of unique elements. So when you put something into a set one time, it can only go into a set one time. What is that like? Well, let's say we're keeping track of names of people in a classroom. If we're only using first names, and there's already someone in the class named Lisa, and we try and add someone to a set, and we try and add another Lisa, that doesn't work, because a set can only keep track of one particular string instantiation, so Lisa. So if we wanted to keep track of multiple people that had the same name as Lisa, instead of keeping track of the name, we'd have to keep track of first name or last name. Or maybe instead of keeping track of first name and last name, in case there was a duplicate of that, we'd have to keep track of some kind of student ID number. So you have to think through what is it that's unique about your situation if that's what you want to work with. Again, there are two ways to implement sets, a hash set and a tree set, and each implementation has its pros and cons. Generally speaking, hash sets are faster. Okay, and the hash set uses what's called a hash table as its implementation, and a tree set uses a binary search tree as its implementation. Okay, moving down then, a stack is an implementation. Second red block up there. A stack is like a list, but it's more specific than a list. It can do all the things that it can do a subset of the things that a list. It can do everything that a list has to do, but it's designed to work in a particular way. It's designed to be a list that you only add things to the beginning of, and you only take things off the beginning of them. And so this would be like if you had like a stack of pancakes or a stack of books. You put one on the top, but the only thing you can take off is the thing that you last put on the top. If you want to take off the thing at the bottom, you first have to remove everything from your stack to get to the element on the bottom. Well, why in the world would you want to do that? Well, it depends a little bit on the problem that you're working with, but sometimes keeping track of things in a stack actually ends up being a really great way to order your information. For example, if you wanted to, basically it's called a last in, first out queue, meaning the last thing that you put in is the first thing that you take out. And so anything in the world that you work with like that is modeled well with a stack. So what would be something that works like that? Can you think of anything that would be like that?
You can order stocks to buy them so that any stock you buy last is the first stock you sell.
Right. So that would be a particular way of managing stock sales. You want to make sure that the stock. Well, let's see. That would be a little bit different. So that would be actually a queue. So the last things you bought were the first things. Is it the last thing you bought is the first one you want to sell? Yeah, you can do both orders. Right. So you could sell things in stack order if you wanted to, where the most recent stocks that you purchased are the first ones that you sell. Different way. Not necessarily. That's a decision though. That's not sort of dictated by the data. Let's see. Off the top of my head, what would be a situation where you can only if you had a storage unit, like a physical example would be a storage unit or a garage. When you put something into the back of the garage and then you fill up the front of the garage, if you want to get the thing at the back of the storage unit or the thing at the back of the garage, everything in front of it's got to come out before you can get to the back. It's kind of a physical representation of what a stack is like. A queue is the opposite. So a queue is an interface, but it is like a stack, except that the first things that you put in are the last things that you get out. And this is like a bank line. So the last person that gets it, like the first person that you take out of a line, the first person that you service at a McDonald's or a bank or something like that, is the person who arrived there. Let's see, the last person, last in, last out. So you just service people in the order that they arrived, basically. So you can put people in at the end of the queue, but you only take things off at the front of the queue. So this is like a pipeline, something that moves through in a flow, through a pipe, through an order, anything like that. A priority queue is a specific implementation, and this is a little bit different. This is when you add things into a line with a particular priority. This is like putting someone into a line to get onto a plane, and you associate with them a priority. So you say first class or coach class or economy class, and the people that get on the plane first are ordered by their priority, not by the sequence in which they arrive. So you can put people in any order you want, but the order in which you get them out is by priority. So whoever is first class comes out before anyone else in the next level down. So that's a data structure that's available for us to work with. Okay, going to go through all of them before we start working with one. But the last set is slightly different idea. The idea of a map is not about a collection of items by itself. It's about relating two items together. So I kind of like the idea of calling it a dictionary because a dictionary suggests a little bit more about the structure of what a map is. A map itself in Java is an interface, and what it is designed, or the behavior that it captures, is relationships between keys and values. So in a dictionary, this would be a relationship between a word and its definition. If we were to do that in Java, it would be a relationship between a string and a string, because we keep track of the word as a string, and we keep track of the definition as a string, and then the map would put those two things and put them together in a pair and keep track of those pairs of items. So maps are for keeping tracks of relationships between objects of different types. And then when it comes time to implement it, we can use either hash map or tree map in order to keep track of those, and they also have their own positives and negatives. Okay, total data dump on you guys. We need to work through all these. Let's look at lists now. Any questions about what I've said so far before we look at one in particular?
So how exactly are hash maps and tree maps and hash sets and tree sets different?
In maps, the keys are unique. And so when you think of a map, all the keys form a set. And so the fact that there's a hash set and a hash map and a tree set and a tree map reflect the fact that both of them have sets underneath them. So a map is like a set mapping to something else. A set is like a set with no mappings. So a hash map takes each one of the keys, or a hash set takes each one of the elements, and the implementation, it groups it together by a digital fingerprint. So it takes a digital fingerprint of a book and says, we're going to keep all books like this together. So if you think about it as books on a bookshelf, you might say we're going to keep the books that have the same color all together. And so when we want to go find a book, we say, well, what color book is it? Yellow. So we'll go to the yellow section and we'll find it really quickly that way. But a tree map or a tree set keeps track of things in order, and that takes a little bit more computational power. And so that would be like when we put a book on the shelf, we're going to put it in alphabetic order. And so when we want to find that book, we know exactly where to look because of alphabetization. Why does that sound wrong? Is that right? Alphabetization? One of those words when you say it out loud, something sounds wrong. Alphabetical, that's what it is. Alphabeticalization. So if you think about grouping things together in color, it's a little less strict than putting things in specific lexicographic order. And so because of that, your hash maps and your hash sets are a little bit more efficient. We will look at them in a little more detail under when we open the hood. Okay, so let's work with this a little bit. So let's create a collection. So when we actually use a collection or a map, we've got to specify what it is we're going to be storing in it according to type. And this is a pattern called generics in Java. And so let's take a look at the slide here and let me point out a few things that are going on. So this is a small class called examples. We have one main method. And in that main method, I just have an example of using these different technologies. So for starters, what I've got here is I've got a definition of, right here, I've got the definition of a variable whose name is names. And the type of that variable is a collection. And the collection contains strings. Now I've declared that variable, but right now it's equal to null because there's no data that it's referencing. In the next line, I say names is going to equal a new array list of strings. So what I'm going to implement that collection with is with an array list. Because names is of type collection, the only methods that I get to use on names are the ones that are common with collection. If I wanted to use other methods that are common with list or with array lists, more specific classes, I would have had to declare names as being of that type. But because an array list is a child of collection, I can implement my collection with an array list. Then I decided to add the string Patterson to my collection. Because add is a method that's associated with collection, and because names is of type collection, I can do that. Collections doesn't dictate the mental model of what we're doing. All we know is that we can add things to it. And then, of course, we can also get the size. So if I ask for the size, I'll get that back as well. All right, so let's try this out together. Let's make a grocery list, and let's use a linked list in order to create it. And so this is going to be a grocery list that contains strings. And so let's see, I don't want to actually do this in a Saros session, but what I'm going to do is I'll do it up here on the screen, and then I'll give you guys a chance to implement it on your own. But why don't you watch me do it first, and then we'll take a break. We'll pause the broadcast and let everyone duplicate what I've done and sort of explore a little bit around it, just so you can see what's happening. Sound okay? All right, so to do that, what we're going to need to do is we're going to need to cut out to Eclipse. We're going to try and make a linked list that contains strings. All right, so here is a class and a main method. And we know that what we're going to be working with is a linked list. So I'm going to create a variable, and we'll call it the grocery list. And this is great. It's a variable name, but I haven't given it a type yet, and so I need to give it a type. Because I know I'm going to implement it with a linked list, I have several choices about what kind of type I want to declare it as. I can declare it as a collection, I can declare it as a list, or I can actually declare it as a linked list specifically. I think that because what I'm thinking about in terms of what a grocery list is going to be, is an ordered list of elements, I'm going to go ahead and call it a list type. That's an interface, so I can't instantiate it as a list, but I'll keep track of it as a list. And we know that it's going to contain strings, so I'm going to use the generics syntax with those angled brackets to say what's going to be in it. Now the first thing that happens is I get Eclipse complaining because it doesn't know what list I want to use, so I'm going to use my command 1, and Eclipse is going to suggest that I import one of two possible lists. So here you see an example of there being two implementations of lists that Eclipse knows about. One is in the package java.util, and the other is in the package java.awt. You have to know that the Java Collections framework is part of the java.util package. That stands for utilities. The java.awt package is a graphical user interface package, and so that would be more like a drop-down list. And that's not what we want in this case. So I'm going to go ahead and import the java.util list. So on line 3, we see that pop up. And just to prove a point, I'm going to end that line there. And so now I have a variable called grocery list that hasn't been instantiated with anything, but it exists, and we know what Java knows what its type is. I'm getting a warning because I'm not using it. And so Eclipse recognizes that Java and Eclipse together recognize and are telling me, hey, you might have a mistake in your code because you declared a variable and you never used it. I'm just not done writing my code yet, so chill out, Java. Okay, so grocery list, before I can do anything to it, I actually need to provide it an object that I'm going to work with. We said that what I wanted to do was to create a linked list of type string. That's going to compile fine once I include linked list. And I use the right syntax. And I use the word new. There we go. Okay. So it's asking me to import which version of linked list. There's only one, Java util, so I'll include that. And that's going to compile fine. So now when I want to use grocery list, even though I implemented it with linked list, because it's declared as a list, I can only use those methods that are known in list. Because I'm declaring grocery list as list, I could have also done this. I could have also said the grocery list is a new array list of string as well, because both of those implement, once I import it, both of those implement everything that list has to implement. They implement more, but they implement at least list. But we said we're going to keep track of this as a linked list. So now I've got it. So now I can add my different elements to it. You can see all of the methods that are associated with the list class and its parent classes there. So let's add a new element, bananas. Great. And then let's also add, I'm trying to remember what was on my slide, apples and milk and ramen, I believe. So now, using the behavior of a list, I've added 4 things to it. And because a list is ordered, that order has been respected. And so if I want to understand what's in my list, I now have all the methods that are associated with the list to manipulate it. So the most straightforward one would be to say system.out println, just so I can see what's happening here. I can't type. Getting over a cold and it's affecting my fingers. So how many elements are in there? Well, we are going to ask grocery list to tell us how many elements are in you. Okay, we can ask about size. That's great. List also enables us to ask what specific elements by index number we have. So I could also use the get method and say the first element in my list is, and so now I'm going to ask my grocery list, well, what is my first element? It's going to be get sub 0. I'm going to get the element at position 0. Again, a list is indexed by 0 first. And so if I want to find the last element in my list, well, I know there are 4 elements in my list, so I could do it manually and say there are 3 here. But if I wanted to be more flexible and not think about how many elements were in my list, I could embed a call to size in there. Now size is going to be 4, and I'm 0 indexed, so I got to subtract 1 from it. So now if I run this, all goes well. You can see my list contains 4. Maybe I should have said 4 items. My first element in my list is bananas, and the last element in my list is ramen. That ordering has been respected. And just for the record, we can actually add things multiple times. So let me add apples to the end of my list and rerun that. So now we have 5 elements in the list. The first element is bananas, and the last element is apples. It's not alphabetic. It's whatever order I put it in. It can contain duplicates. The list is responsible for remembering the order of things that are present. This is the behavior of a list. The behavior is enforced by its implementation, by the contract that it's given in the comments for its public interface, and then by the methods that it exposes as part of its public interface. Questions about this so far? Online? Okay. So what I'd like us to do then is to take a second and I'd like you to build a list, but why don't you guys try and make an array list? Do a grocery list as well. Add 5 elements to it that you want to, and try and create a for loop that's going to walk through each element of the list and print out the elements of the list in order. Does that make sense? Okay. So I will, let's see, how should I do this? I'm going to cut back to the slide, and I'll work with you guys individually. We'll come back in maybe 9 minutes at 11:20, and we'll see how we did. Okay. Bring the slides back up and go offline for a sec. we're still bashing our way through this, and so we're going to take another 5 minutes to try and make sure we get a good solution. Things we're running into here are just the syntax of actually creating a new array. That's new to a lot of us. And I guess just the details of that. So we'll be back in Okay, we are back in, and we are going to walk through our array list implementation. Everyone in class was able to get to the point of making an array list and putting stuff in it. About half of us got through doing a loop over the elements, and we had a couple different ideas about how to go about doing that. So let me walk through a specific way of doing it, and I'm going to make some space here. What I'll do is I'm just going to quickly change this to an array list. So I've created a variable that is of type list. I could have also made this array list. Maybe for now it's a little bit more straightforward to just say that it's the type of grocery list is the same type as what I've instantiated here. I went ahead and then add 5 elements to it. I print out its size, and I can get the beginning and the end. If I want to go through all the elements in it, the straightforward way right now is to create a for loop and say I'm going to create an integer, something of type integer called index, and that's going to start as 0. So that's my starting condition for my loop. I'm going to continue through my loop as long as index is less than grocery list.size. And each time at the end of my loop, I want to advance my index by 1. That will have, in this case, index is going to be an integer. It's going to go through the numbers 0 through, in this case, 4, because I have 5 elements in my grocery list. And now I'm going to use those numbers as indexes into my list in order to pull the element out. So what I could do here is I could say, I'm going to copy that. I'm going to say, I'll print out the index. I will say like the first element in my list is grocery.getIndex. So now when I'm doing this, I'm responsible for walking through the list and getting each of the elements from it. I'm using the index I to be an integer, and I'm using get to pull out a particular element along the way. So when I run it there, you can see that I get the 0th element of my list is bananas, then apples, then milk, then ramen, then apples again. So in that way, I'm able to pull all the pieces out along the way. Now, one person in class used fast enumeration. That's something that's pretty common from Python. Java also has fast enumeration, and I'll show you how to do that in a couple slides forward. I want to introduce iterators before we do that. Okay. Any questions before we move on? You guys feverishly copying? So what I want to do now is I want to talk a little bit about the difference between these two. So when I drew these pictures, I actually intentionally drew these pictures differently. Just went back a slide. So on this slide, I described a linked list. And you can see that the elements in the linked list, bananas, apples, milk, and ramen, have those arrows between them. Those are like the people holding hands together. Those links are references to the next element in the list. But when I implemented it as array list, I used this long array of 8 elements, and you can see that there are 8 slots there, but only 4 of them are filled in this diagram. That's because array list is doing something similar to this. It is allocating 8 spaces and putting things in those spaces when it comes time to keep track of them. Well, there's advantages and disadvantages to using each one. Like I said, a linked list works like a chain of people holding hands, and an array list works more like a carton of eggs, where the data that we're trying to keep track of in the first metaphor is people. The people represent the objects, and in the second case, the eggs represent the objects. The first representation, the hands are representing the connection between each individual element, but on the bottom, we can assume that each one of the slots in the egg carton has been numbered, maybe 1 through 5 across the top, and maybe 6 through 10 across the bottom. What kind of egg carton has 10 elements in it? I don't even know what I was thinking there. It's like I don't know. It seems like a good idea, sort of, until you start talking about dozens of eggs. It's at least decimal. I don't know what's going on there. Wow, my whole world's falling apart. Okay. In any event, if we consider that the array list reserves space to keep eggs in, then we can keep up to 10 elements. But if we need to keep more than 10, we need to get a bigger egg crate. And so we have to take some time in order to get a bigger carton of eggs. So because of that, a linked list is very efficient at adding things in the middle of the list. Because the only things that you need to change in this list is you just need to have 2 people let go of their hands and grab onto the hands of the new person that you're adding into the middle of the list. Visiting the elements in order is very efficient because as you walk down your list of people holding hands, you can visit each person just by following the chain of hands, even if they snake around in a crazy pattern. Visiting elements randomly in that chain of hands is a little bit difficult, though, because it might be hard to know which person is the third or the fourth element in that chain of hands, especially after you've been adding and removing people and maybe the chain of people are going all over the place. And an array list, in contrast, adding things in the middle is fairly inefficient, because if we want to add an egg to the third element in that egg carton, and we want to preserve the order because order is important, we need to shift all the eggs greater than position 3 down 1 in order to make space. And that shifting actually takes time in an array list. Visiting elements in order is efficient also in an array list. And visiting elements randomly is efficient because it's very easy to predict where the fourth element or the 10th element is going to be, the 9th element in this case. So what I would like to do is I'd like to try and compare these two things by actually doing timing of them. And so I'm going to write some code that's going to try and add a bunch of elements to a linked list and add a bunch of elements to an array list so that you can see the difference in timing between the two and to understand that the implement, even though both of them abstractly can understand the difference between, both of them abstractly can handle the same operations, they might not necessarily do them at the same speed. All right, so let's see. To do that, let's cut to Eclipse. And I am going to create two elements. The first element is going to be my array list. I'm going to call that array list AL for array list. And then I'm going to create a linked list. I'm going to call that LL for linked list. And I'm going to initialize the two. I'll say AL is a new array list, and LL is a new linked list, and both of them are going to contain strings. All right, the next thing that I'm going to do is I'm going to populate these lists. I'm going to populate them with a lot of elements. And I'm going to do this, it's going to be, I'm just going to put random data in it for now, but I need to get a lot of elements in it. And I need there to be enough data that when we add things, we can actually see a difference in time. Because if it's just a small number of elements, then the difference in time is going to be so minuscule that we're not going to notice. So I'm going to go ahead and create a list. Maybe we'll try 500,000 things. So I'll create an integer I that's equal to 0, while I is less than 500,000. We'll do I plus plus. And we'll create the thing that we want to add. And the thing that we're going to add is going to be, we're filling it up with strings, but let's go back and let's actually fill it up with integers. There's no reason why we can't fill it up with integers. So instead of keeping track of strings in each one of these things, we're going to keep track of integers. And the integer that we're going to add to it is going to be I itself. So in a really boring array where the first element is going to be 0, second's going to be 1, all the way up to 500,000. So now we have two arrays implemented with different technologies that contain the same data. And now what we're going to do is we're going to do the timing aspect of it. What we'll do is we'll add another 500,000 elements to the beginning of each one of these arrays. And that's going to be relatively fast for the linked list because it just means that we're going to have to break off the hand of the first person and add a new person in. But for the array list, we're going to have to shift everything down into that carton of eggs to make space. So let's create a new list. And we're going to keep track of time by saying system.currentTime millis. So that will give us the current time in milliseconds since January 1st, 1970, Greenwich Mean Time. And in our loop, we're going to go ahead and we're going to add to position 0. Sorry. We're going to add to position 0. And the element that we're going to add is going to be I. So we're going to add the number 0 through 500,000 again. And then after we're done adding all those elements, we're going to keep track of the time at the end. And then we can say the time to add 500,000 elements to an array list was, and we will add the end time minus the start time. How many milliseconds? Since 1970 should be higher, so end should be a higher number. So end minus start should be the amount of milliseconds that have elapsed. And so we'll go ahead and add a unit in there because we are user-friendly. Okay, so that's our first experiment, adding 500,000 things to our array list. Now let's do the experiment again, but for our linked list. Okay, I'm getting an error because I don't need to declare start another time. I just need to use it. So I'm going to I'm going to delete it. I'm going to overwrite start with the new current start time. I'm going to do a loop that's very similar, but instead of adding it to the array list, I'm going to add it to the linked list. And then I don't need to declare end again. I just need to use it again. So I'll get the end time. And then I'll say the time to add 500,000 elements to a linked list was however many milliseconds we've got. So now let's see how this goes. We'll run it. And I didn't do a cooking show thing beforehand. I didn't get this all ready to go. So maybe 500,000 is actually too much. Fair enough. It looks like 500,000 is going to be too much. Let's take it down to 10,000. Put 10,000 elements in it to start with, and we will add 10,000 elements to it. There we go. All right. So to add 10,000 elements to an array list took 23 milliseconds, and to add 10,000 elements to a linked list was 3 milliseconds. Huh. That's interesting. There's a significantly more time to do it with one over the other. Let's try cranking up that time a little bit. Let's try 50,000. Oh, what did I do wrong? There we go. So adding 50,000 elements to the beginning of an array list took 784 milliseconds, almost 1 second, versus 4 milliseconds. Well, now we're starting to talk about, I mean, it's not an epic, but we're starting to talk about some human noticeable times. And 50,000, it's a big number, but it's not big in terms of the way the internet is big, right? So the right implementation here can make the difference. Well, from this, you would think that, oh, we should use a linked list. That should be the obvious answer. But maybe that's not the task that we have. Maybe the task isn't adding a bunch of things to the beginning of an element. Maybe we want to check maybe we want to check each individual element, like I said, randomly, and see what the value is. All right, so that means that our next task is going to be a little bit different. Let's comment out this code. And now what we're going to do is we're going to randomly check. Let's pull some code out here. We're going to ask for what a particular index in the array is. So it's like we're going to look up a particular index. Now we know what the indices are because we added them one at a time and we added them to the end. But let's just do 50,000 lookups, and we will create a random number. We haven't really talked much about random numbers, but we'll say r equals a new random object. And we'll import that from Java util. And each time through the loop, we'll say my index is going to be equal to r.nextInt, and we only want to go up to 50,000 because that's how many elements are in our array. If you look at the documentation for nextInt, it's going to give us a number between 0 and 1 less than 50,000, so that's perfect for looking up elements in an array. And then we're going to say our value is going to equal the ArrayList.get element index. So we're going to look up that element, and we're randomly choosing it. We'll store the value there, and we'll say if value not equal to index, because if we look up the 10,000th element, it better be equal to 10,000 because of the way we created our array. We'll throw a new exception. we'll just have an error. If I wrote my code right, I might have a bug in it. But if I wrote my code right, then this runtime exception will never get thrown. But what this is going to force us to do is just look up 50,000 elements in our array list. Okay, and then we have that. And so then we'll say the time to look up 50,000 elements in an array list was this. Now let's do the same thing for our linked list. We'll pick random numbers. We'll get something from our linked list. We'll calculate our time. And the time to look up 50,000 elements in a linked list was. Okay, in our previous experiment, we saw that an array list took a lot more time to add elements to the beginning. So array list was bad, linked list was good. Now when we run this experiment, something went wrong. Okay, what did I do wrong? Let's see, index. Take a look what happened here. 28. Okay, we actually ended up throwing this exception, so let me see. Walking through it on line 18 through 20, we added integers to our array list. Add should be adding to the end. Did we do that right? Add it to the end of the list. Okay, so we have a fresh list. We're adding 0 through 50,000. We're coming down here. We're doing a loop, and we're saying, give me a random number between 0 and 49,999. Please give me the value that's at that index. It should be equal to the same thing. Something went wrong. So let's see what we actually got out. So right now I'm debugging because I don't know what exactly happened. Let's run that, see what happens. Something went wrong. I got a 32216 when I looked up 32116. Oh, well, that's because I've got objects, and I did exactly what I said we should never do. I think that's what let's run that, see if we get things done. Great. Okay. All right, so previously we saw that an array list was worse, and so now we're running the lookup code. The time to look up 50,000 elements in an array list was 24 milliseconds, and the time to look up 50,000 elements in a linked list was 2,000 milliseconds. So wait a second, what does that mean? We could now uncomment our code from our previous experiment. Run the whole thing together. The time to look up 50,000 elements in an array list was 21 milliseconds. The time to look up 50,000 elements in a linked list was 2,265 milliseconds. The time to add 50,000 elements in an array list was 660 milliseconds. And the time to add 50,000 elements to a linked list was 8 milliseconds. So the implementation makes a difference depending on what your operation is. So some operations are faster in an array list than they are in a linked list. And some operations are faster in a linked list than they are in an array list. So what that means is you may generally have this idea that you would like to keep track of your data in a list, like your grocery list, for example. But you might also be thinking, well, I want this to be efficient. Am I going to be doing more lookups, or am I going to be doing more adds? Because depending on whether I'm looking up data or I'm adding data, I might choose one implementation over the other. Now again, you saw that this only really made a difference when I started getting up into numbers in the thousands. If you're keeping track of a grocery list that has 10, 20, 100 elements on it, you're not going to see any perceptible difference between using an array list and a linked list because the numbers are just too small. It's only when you start getting into larger numbers that they start making human perceptible differences. But they are differences, and the implementation makes a difference, even though both of them can do everything that a list can do. That's an important observation. Questions about that? So it's a really important concept to try and get across. And it's something that maybe it's going to take a little bit of time to sink in. So we compared the two, and depending on whether we decide to keep track of things like chains of people or by egg cartons, it made a difference in terms of ordering. We said that both of them implement the list interface. Well, it's actually the case that linked lists has very specific methods that are only applicable to a linked list. It has all the ones for collection. It has all the ones for list. It has some specific ones like add last, add first, get last, remove first, and list iterator. And so you can only call these on an object if you've declared your variable of type linked list as opposed to type list or something else. When we took our break last time, and I asked you guys to implement a small grocery list with 5 elements, one of you decided to go through your list and you naturally tried to implement your printing of your list as fast enumeration that comes from background using Python. Java also has fast enumeration. And so in order to do fast enumeration, I need to show you how this works in terms of an iterator. An iterator is a kind of object that helps you walk through all the elements of a list, and it keeps track of where you are in that list. You can think of it a little bit like a cursor, keeping track of a position in your word processor as you move down the line. An iterator is a class that does that. So here's some code that implements this iterator. A list iterator is something that iterates over a list. And so we can declare a list iterator like we have here with variable I. And because our list iterator is going to walk over a list that contains strings, it is a list iterator, and in angle brackets we put strings. To kick it off, we have to ask the list, please give me a list iterator. So when we say names.listIterator, that is asking the linked list to give us an iterator that we can then walk over. Give me a cursor so that I can walk over the list that you represent. Once you have that, the two primary methods that you call hasNext, which is a true or false. We either have a next element or we don't. And as long as we have a next element, then we can get the next element by calling I.next. When we do that, we walk over the next element, returning it, and then we can do whatever we want to do with it. In this case, we're just printing it out. So if we were to do this visually, we could imagine taking our list of people. That would be names in the code here. And then when we say names.listIterator, I becomes that arrow. That red arrow is now I. When we say I.hasNext, we're asking, is there a person to the right of my arrow, such that if I call I.next, I will be able to see who that person is? Right now, the answer is true. There is something next to that arrow. So when I call I.next, the iterator steps over that person and returns the object that it just stepped over. So in the first time through this iterator, S gets assigned to that first person on the left side. And the iterator kind of lives in this halfway position between two elements because we're going to ask, is there a next element? Does this list iterator has next? Is I.hasNext true? And in this case, it's true because that person with the little hat on it is next. And so when we call next, we step over that person, and S is assigned that person in our loop. I.hasNext is still true, so we step over. I.hasNext is still true, so we step over. I.hasNext is still true, we step over. The last person in that list gets assigned S. We do something with S. We system.out.println S. Now we ask, is I.hasNext true? It's no longer true. We've consumed all of the elements in our list, and so if we ask the iterator if there's another element, it will return false, and we will leave this loop. So we can use that iterator to step over each one of the elements in turn if we want to. Turns out that the list iterator has a few more methods. You can actually go forward and backwards. So there's another method that says hasPrevious. So if you want to switch directions in the middle of it, the iterator gives you the ability to do that. The iterator also gives you the ability to add things in the middle or to remove things in the middle. So I want to demonstrate that, and I'll demonstrate that with code on my own here. And then I'll show you how we can use this for fast enumeration. Okay? So here we go. What should we do? Let's copy this. I'll stand by. Let's create a new linked list. I'm just going to call it L. Let's call it names. It's a little more clear. And we'll set it equal. We have a good variable, but now we have to instantiate it. So we have to say new linked list. And I actually want to keep track of strings in here, so it's going to complain because when I declared it, I said it holds integers. I'll say it holds strings. And now I'm going to add a couple names to it. Hey, royal wedding. Let's add some royal wedding names to it. Well, Megan. Megan with an H. And who else was at the wedding? Harry. No one else? William was there. Bishop Curry was the hero, so I'm going to say Bishop Curry. All right, 4 is good. There were 600 people in the church and 1,200 people outside, but who's counting? And so here we've got a list, and now what we're going to do is we're going to ask for names to give us a list iterator. And that's great, but we need to capture it in a variable. So I'm going to do that, and I'll just call it iter for short. All right, so now when we start here, we have Megan, Harry, William, and Bishop Curry, and our iterator is at the beginning of those 4 elements. And so if we ask iter.hasNext, that's going to return true. But we know it's going to return true, so I'm not going to ask that. Instead, I'm going to capture what the first element is. And I'm going to say iter.next. And that's going to be equal to Megan, or person will be equal to Megan. And the new situation will be that there'll be Megan, and then the iterator is between Megan, Harry, William, and Bishop Curry. So the vertical bar represents the iterator. Now if I do that again, I don't need to declare person again. I just need to use it again. Now person is going to get assigned Harry, and the iterator is going to be put after Harry. Do this again. The person will be equal to William. Move the iterator to there. Person will be equal to Bishop Curry. And the iterator will now be at the end. And now hasNext will be false if we wanted to do something along those lines. So let's just see that in action. Let's print it out so that we can, well, actually we don't need to print it out. We could just use the debugger. That's kind of fun. And we can run this, debug this as a Java application. Okay, so I'm going to double click here to go to the code that's being run. There we are, having added names to our linked list. We can come up here and look at names, and we can see a representation of the 4 names that are present. And as we step over this code, we can grab the first person by stepping the iterator over our first person, and person is now Megan, as we expected. Step over that line of code, and now person equals Harry, highlighted in yellow. Now person equals William, highlighted in yellow. And now person equals Bishop Curry, highlighted in yellow. If we add an expression, we ask iter.hasNext, is that true? Well, we can see, if I can get this on the screen, we can see that that has the value false now. So we can use an iterator to step through our code and do things along the lines. We can, do other things as well with our iterator. Our iterator gives us a lot of power. So we can also say previous. Spell it out all the way. And in this case, we went from being here, and now we're stepping back and moving before Harry. And so now we get Harry again if we run through that code. Debug it again. Step over. You can see iter.hasNext is true over here. Names is all of our names. And as soon as we declare person, we'll get to see person. There we go. So we get Megan, and then Harry, and then previous. We step back again. Person is still Harry because we step backwards. Did I update this right? No, sorry. This should be, we're going to get Harry. Where are we? Got lost. Here we are. Okay, so we did previous, so we step back, and next. So after we run this line, we're going to get Harry again. Boom, person is still Harry. And now we're going to go get William, then Bishop Curry. And now has next is false up here. The last thing that I want to show you running with this iterator is you can use the iterator to add things in the middle as well. Come back to our Java perspective, and we come up here to our code, and we say, oh, you know what? We totally forgot Kate. Ah, that's tragic. So what we can do is down here, after we step over William, we can say iterator.add, and we can add someone into the middle of our linked list using the iterator. Sorry. That's not going to return anything, but it should change our lineup so that now we have Megan, Harry, William, Kate, and then Bishop Curry. And what happens is when you add something to our linked list, it gets added before the iterator. And so now as we step over, we should see this. Make sure I didn't make an error there. Started our iterator, step over those. We get Harry, Harry, we go back. We get Harry, we go forward. We get William. Now we add Kate, and we see that Kate showed up in our list, added where our iterator is. And we get our next person, and our next person is Bishop Curry, and iterator is false, as false. You can also remove elements with your iterator as well. So the iterator gives you a lot of power to, like a cursor, just like a cursor in a word processor, to go through the different characters in your list and delete and add things as you want based on the position where you're at. Now, why would that be efficient? Well, we saw that a linked list is like people holding hands. And if you want to add someone to the middle, it's really fast if you have an iterator that's right there. But if you have to get to that position, it takes a lot of time to get there. We saw that with our array list. Array lists are very fast to get to a specific position, but slow to add something. Linked lists are slow to get to a position, but fast to add something. So that's why there are two implementations that are possible there. Okay, so where that puts us is finally we have array lists, we have linked lists. Those are both implementations of lists. Both of them give us a list iterator through which we can step through each of the elements of our array. The last thing that an iterator enables us to do is it enables us to do fast iteration. So this is if you want to go through a list, you want to go through the entire list, you want to go through the list from forward to backward, and you don't want to do anything tricky. You don't want to add things, you don't want to remove things, you don't want to stop in the middle. You just want all the elements. And you don't want to deal with indexes, you don't want to deal with the count of the element you're on, you don't want to deal with the iterators, you can just do fast enumeration. And this is the way that you do that. This is a different kind of for loop. It's different than the three that we previously introduced. Previously, we introduced while loops, for loops, and do while loops. This is a different kind of for loop, and it's kind of straightforward. The way it works is you have on the left side of the colon, you have a variable that represents the different elements that are in your collection. So names is a collection of strings. And so S is going to be equal to each string. Each time you go through the loop, S will be set equal to the next element in your collection. And so you can do whatever you want to do with S. The thing that's interesting about this is you don't have to know how names is implemented. It could be a set, it could be a list, it could be an array list, it could be any number of things. As long as it implements an iterator, you can go through all of those elements one at a time, and this loop structure will do that for you. What's important is the iterator. If your object has an iterator, if your collection has an iterator, then this will work. So this is kind of convenient if you don't want to deal with the index values along the way. Okay, let's take a moment and let's go back to the grocery list that you had. And if you haven't already implemented it with a fast enumeration, but if you implemented your printing out of your list with a for loop, try doing a fast enumeration like we've got on the screen here. If you did do a fast enumeration, try going through your list with an iterator. So the ability to go through your list either with indices, an iterator, or with fast enumeration are all three skills that are important to know. Okay, So we'll take a 5-minute break to do that, and we'll come back as soon as we're done implementing fast enumeration in our list. we're coming back. Okay, so we looked at iterating through a list using index values. And for that, we needed to start at 0, go to the size of our collection minus 1, and do get, or depending on how we did our loop, do .get. We looked at iterators, where we made a list iterator, and while has next, do I.next. And then we did fast enumeration, which is what we've got on the screen here. That's 2, 3, almost 4 of our Java collections framework. It's the introduction of collections. It's the introduction of the list. It's 2, implementation, ArrayList and LinkeList. The next one to tackle is sets. Now, those of you who have done Python or are doing Python and Swift or doing Python and Swift in some other language, Java, you know that these collections frameworks in Java are present in all languages. Most object-oriented languages have similar ones. So a set is a common one as well. And a set is similar to a list in that it's a collection, but it's different than a list because it keeps track of things unordered and doesn't allow duplicates. And so I was trying to figure out what a good image of this would be. And so I was kind of thinking like a basket of vegetables or fruits where the order doesn't matter. You just put one of everything in, and then you have this big bag of stuff, and you know it's there or it's not there, but the order isn't that important. So it's like a little bit like once you have your grocery list and you put everything into the cart, you don't care about the order, you just want to know that it's present. So sets are kind of a representation like that. We have 2 implementations. We have the hash set implementation and we have the tree set implementation. Most of the time you're going to want the hash set. Hash sets implement the underlying functionality of the set by, this is the implementation, not the user, not the application programmer. So an application programmer, you're just adding things, checking if they're present, removing things, stuff like that. But when you implement it, well, how are you going to keep track of that for the application programmer who's using it? You can use a hash set or you can use a tree set. A hash set is the one where it sort of groups everything kind of together so it knows roughly where to look, like keeping books together by color or maybe keeping vegetables together by color. That way you know where to look to see if it's present or not, but the exact order doesn't matter. A tree set actually keeps everything in order. The set doesn't expect that, but in order to implement it, we keep it in order, but we don't keep it in a linear order. We don't keep it in a linear order like a list. We keep it in this fancy tree structure that enables us to access things quickly, called a binary search tree. Actually, it's a balanced binary search tree. In order to actually store something in a hash set, the object itself must implement 2 methods. It must implement the hash code method, and it must implement the equals method. These are common in most objects that you would want to store in a hash set. But if you're making your own object, if you're creating a rectangle class, or you're creating a car class, or you're creating something you're interested in, and you want to make a set of them, then you're going to have to implement hash code and equals on your object. Now, fortunately, Eclipse has Wizard that will do this for you. It's really powerful little feature. Tree sets, in contrast, have to implement compare to. So a tree set requires you to be able to put everything in a particular order, like we looked at with the string class in lexicographic order. So strings can be kept in a tree set because compare to is implemented on strings. Regardless of which implementation you use, they're both going to implement the contract of the set, which is keeping track of things uniquely but unordered. Hash set is usually your default choice in implementation, unless you know you're going to want to visit the elements in your tree set in the natural ordering, so the lexicographic ordering or whatever ordering you have. Now notice that this ordering is not the order that you put them into the set. That's not what we're talking about. And a list keeps track of them in the order that you put them in. A set just keeps track of whether things are present or not, and a tree set will give them back to you in the natural ordering, but not the ordering that you put them in. Lexicographic order or whatever compare to does. Okay, so let's try out sets together. And, oh no, let's not try out sets. Let's start next class by trying out sets because we're out of time. So let's see. Right. So given that we're out of time, let's just run through what it is that we were able to do today. We introduced the idea of the Java collections framework. We spent some time looking at lists, ArrayLists, and LinkeLists in particular to make clear the point that implementation matters in terms of runtime. Small projects, no big deal, but bigger projects, the difference might matter. And then we started talking about sets. And we'll dig into sets more next time. Overall, what these Java collection frameworks allow us to do is keep track of collections of objects in different ways, in different orders, and different properties, so that we can do more higher level data processing on them along the way. Any last minute questions, remote participants or otherwise? Awesome. All right. Thanks for your attention today. And we will got a lot to do this week, so you'll stay busy, and we will see you tomorrow, if not sooner. So thank you very much.